Hi, welcome to this lecture where we will work out the solutions of the probability assignment, assignment 1. Of course, it'll be a good exercise in solving problems as well. So let's go over the problems one by one. There are 5 of them. The first one is a problem in binomial distribution where you have 2 variables x and y. One of them is with parameters n and p. The other is with parameters m and p. Okay, and they're both independent. You have to show that if you add the two variables, random variables. I think in the problem I called it by another name. I called it z. You have to show that this new random variable is also a binomial, also follows binomial distribution with the parameters n plus m and p. The second parameter remains the same. So the way you can do it is, if you go back to the lecture where we had learnt about binomial distribution, we said that if x was following binomial distribution, it meant that you could write x as a summation of n independent Bernoulli variables, random variables. Okay, so x you could, because this is up to n, so n trials. Okay, so there are going to be n Bernoulli trials. So each of these are, so xi are Bernoulli random variables with parameter p, each of them, and they are IIDs. In other words, they are independent and identically distributed because they're all following Bernoulli p. Okay. Similarly, you can write y. It's the same thing, but with parameter m. So they are going to be m variables, m random variables, which are also Bernoulli p and also IIDs. Okay. So what is going to be x plus y? Really, all you have to do is to just add the 2. So they turn out to be x1 plus x2 plus, this goes on up to xn plus y1 plus y2 plus up to yn. And you can see, because all of them are Bernoulli random variables following Bernoulli trials with parameter p. So these are going to be, so all of them are, they are IIDs. Each of them are IIDs, and because x and y are by themselves independent to each other, any xi and yj from here will also be independent. So in that sense, you're going to have all the xi's and yj's from here. They're all Bernoulli trials, and they are IIDs. And that's the definition. That's really the definition of a binomial distribution, or a random variable following binomial distribution, that if you can express the random variable in terms of m or n or k Bernoulli trials, then it would follow binomial np, okay, n or m, whatever the number of trials are. And since this variable can be expressed as a sum of such n plus m Bernoulli trials, and each of them are IIDs because they were IIDs from before, so therefore this implies that x plus y will be a binomial, will follow a binomial distribution with parameters n plus m and p. Okay, that's it. That's all there is to this problem. Okay, it's absolutely a problem of just going by the definition of what a binomial distribution is. Anything that can be expressed in terms of n or m, trials, Bernoulli trials, all independent, that itself is a binomial distribution. So therefore, that's the first problem. Okay, right. Let's do the second one. The second problem says, so here it is. I'll rub this one out. Problem number 2. this one says that you have a discrete random variable. Oh, first of all, we have defined what is called a Poisson distribution, or a random variable following Poisson distribution. So we said that a random variable x, okay, would be said to follow a Poisson distribution. It's a new kind of distribution. It's a discrete distribution. If the spectrum of x is like binomial, where binomial ends with n, but Poisson just continues. Okay, there is no ending to it. So if you have a random variable whose spectrum is an infinite set, but it's a discrete set, okay, and if the PMF, or the probability mass function, which is of course written as probability x equals k, because k is one of them from here, one of the spectral values. If it is given by this particular formula, okay, e to the power minus mu, mu to the power k by k factorial, okay. So if you have a random variable whose probability mass function is defined like this, or follows this kind of a formula, and its spectrum is a countable but infinite spectrum like this, in that case this is called a Poisson distribution with parameter mu, okay. So the question here says that, let's say that if you have a random variable which is following a binomial distribution with n and p as parameters, okay, but n is very large and p is very small. In other words, n goes to infinity and p goes to 0, okay, in the manner that np is constant, okay. So n here, so we're doing a problem, for example, where the number of trials is very large, but the probability that the outcome is possible, the probability of an outcome in each trial is very small. But the product is a constant, okay. I mean, you can have two numbers, which one of them is really big and one of them is really small, but the product is a constant. For example, n can be, you can have this one as n, and maybe the probability decreases as 1 by n or mu by n, okay. Then if you multiply this by n, okay, so n, it doesn't matter how big n is, the probability is still very small, okay. So it decreases according to the order of n, okay. In that sense, you can have np as a constant, okay. So now the question here is, show that when this happens, that when in a binomial trial, the number of trials becomes very large, but the parameter p becomes very small, you have to show that this binomial random variable slowly approaches a Poisson random variable. In other words, the PMF of the binomial distribution, the probability mass function of y is equal to k, okay, slowly approaches, instead of the usual formula where it is n choose k, p to the power k, 1 minus p to the power n minus k, instead of that formula, this slowly approaches this formula, which is e to the power minus mu to the power k by k factorial, and that is probability of the Poisson distribution at x. Okay, this is what you have to show. Let's just show it. So we'll start with the normal formula for the binomial distribution, which, as I said, is n choose k p to the power k and 1 minus p to the power n minus k, okay. This is the same as q, okay, or 1 minus p. Now I just want to write it out in terms of, so I want to break this up in the factorial form. So this is going to be n minus 1 up to n minus k plus 1. And here, because there is a k, you're just going to get a k factorial and an n minus k well, sorry, this factor is not there because this vanishes with the n minus k factorial on from the top. Okay, so this is what you have from here. You have p to the power k, but I don't want to write p here. I can write p in terms of n. I can write p as mu by n. Okay. Let's just write it first and then I'll change it. So n minus k. So I don't want to keep p as it is because p is given in terms of n. So let's write this as mu over n. And this one accordingly is going to be mu over n. It's mu, okay? Let's write it properly like that so that we don't get confused. Okay. Now, what we can do is, we look at the formula. This mu to the power k is there already. And the k factorial is already there. So let's just take them out. I want to take out mu to the power k and k factorial outside. Okay? So I'll adjust the rest of the things. So now here, this is really mu to the power k, n to the power k. Okay? Now I have taken this one and this one outside. I'm left with k n's here. And I have k factors in the numerator. Okay? You can see that. Okay? Starting from 0 up to k minus 1. There are k factors. So I want to divide each factor by 1n from here. So I want to divide n by n. I want to divide n minus 1 by n. I want to go on till I divide n minus k plus 1 by n. Okay. The number of factors actually match with k here. Okay. Starting from 0, it's like n minus 0, n minus 1, n minus 2, up to n minus k minus 1. Okay. And then I have this factor left here, which I can leave it like this, but I will change it a little bit. I want to write this as, I want to break up this index as n and then 1 minus mu by n to the power minus k. Okay, that you just add the indices and you will get this back. Okay, now of course, this is 1. That's just 1. This is, you can write as 1 minus 1 by n. This is, I'll write 1 here. The next factor is 1 minus 1 by n because this was n minus 1 by n. The next factor would be, you can guess, 1 minus 2 by n. And this goes on till the last factor, which will be 1 minus k minus 1 over n. Okay? Now, of course, I need to show that this goes to this Poisson distribution only if n and p behave like this. N becomes very large and p becomes very small. But I have replaced all the p's by n's, okay? So I have no need for n's here. So let's take the limit that n tends to 0. What happens when n tends to 0? Py equals k. This becomes, okay? This becomes what? This becomes, okay, as n tends to, so this is now equal to, but as I take n tends to 0, this will slowly change into, let's change the n's to infinity here. If I change the n's to infinity, this one has no n, so this is what it is, okay. As you slowly change the n's, here, this one is 1 over infinity, that's a 0. This one goes to 2 over infinity, that's a 0. This one goes to k minus 1 over infinity, that's a 0. So all these second terms here from these factors, this term is 0. This term is 0. So you get 1 from here. You get 1 from here. Again, this term is 0. So you get 1 from here, from this one. So all of them give you 1 as you tend n to infinity. So it's just 1 from all of this. I don't even need to write this, okay? The whole thing collapses to 1. What happens to, I'll talk about this, but what happens to this one? Well, it's the same thing as happened to this one. There was a constant factor like 2 and n in the bottom. Here is a constant factor like mu, and there's an m in the bottom. As you take n to infinity, this factor goes to 0, and so you get a 1. So all of them reduce to 1. But of course, I have to. The reason I've left this one out and worked this is because there is no n here. There's an n here. So so this factor is slightly different from this one. This is a constant, so I can just make this 0 as n goes to infinity. So all of them are 1. So I'm only left with this thing where I'm only left with 1 minus mu over n to the power n, where n goes to infinity. Okay, so actually, this goes to, right. What happens to this? Of course, as I have already given in the assignment, I've mentioned this as a hint, that if you have, this is a very famous limit, if you have 1 plus alpha over n to the power n, and if you take n to infinity, this actually gives you e to the power this alpha. That's a standard limit that all science students must know. So this is the same thing, except that here alpha is replaced by minus mu, negative mu, okay? And so this whole thing becomes e to the power negative mu, and you have mu to the power k over k factorial e to the power negative mu, okay? This is not done, it's above, okay? E to the power negative mu, and that's this, e to the power, that's the probability mass function that the Poisson variable will be equal to k. Okay, so therefore, it's just a more than a probability problem. It's just a problem in limits and just writing things out. Working with numbers, and that shows the purpose of the problem is, well, one, to check whether people can work this out. And two, to also give you a hint that if you have a problem in a binomial distribution where n is very large, but p is very small, then we can approximate that binomial problem by a Poisson problem, whose formula is a lot easier to handle than a formula like this. Okay, the binomial PMF formula. Okay, so sometimes when n is very large, so by infinity I don't mean exactly infinity, I mean something that is very large, but p is also small, so that they maintain their product as a constant. In that case, the probability mass function of the binomial distribution sort of acts like a Poisson variable, Poisson random PMF, and so we can approximately give you the answer by not using this. I can give you the answer by this. Of course, it is going to be an approximate answer, but as n becomes very large, this goes towards this, and the error becomes very small. Okay. All right. So that's the second problem. We'll do the third one. The third problem is a problem in expectation, which is problem in averages. Okay. Now we will take up expectation very soon, but it's a way to introduce what is an expectation. It really means averages, and we will talk about that. But I have defined what is an expectation in this problem. And if x is a random variable, it's a discrete random variable. Okay, it's given to be a discrete random variable. We have defined expectation E box X to be this particular thing, okay? This summation of all the probability mass functions x equals xi's multiplied by xi's, okay, where each xi is from the spectrum of x. Okay, that's the definition. The question is, if y is a binomial distribution, which of course is a discrete random variable, if y follows binomial distribution with parameters np, show that this formula, this whole sum for y, that is the expectation of y, which really means the average value of y, and we will talk about that when we take this up in detail, this will be equal to np, this n and this p. Okay. All right, let's just do that. So we will start with what the formula is. We'll just work out the formula. So this is going to be, so for this binomial distribution, the spectrum is what? It's from 0, 1, 2 up to n. Okay, that's the spectrum of a binomial distribution. This goes up to this parameter n. So each of these xi's are really these numbers, k, 0, 1, 2, 3, 4 up to n. So this, for this binomial distribution, this summation is going to be probability x equals k, okay, one of these k's. Okay, these xi's are just 1, 2, 3, 4 like that. So x equals some k from here, multiplied by the xi, which is a k, and spectrum, all points in the spectrum. The summation is all points. So the summation is, and the spectrum ranges from 0 to n. So all points from the spectrum are from k equals 0 to n. Okay. Right. So let's just do that. Summation k from 0 to, well, actually I can take it from 1, because you see the first, when k is 0, this term becomes 0, because you're multiplying by 0. So this, I can take this to be a sum from 1 to n, and then I will write down what this formula is, because it's a binomial distribution. So it's going to be nck p to the power k 1 minus p to the power, or let's just write q, because it's short. Q is 1 minus p. N minus k. Now let's just write, so k from 1 to n, I want to write, so k as it is, I want to write this in terms of factorial. So you have n factorial, you have k factorial, and you have n minus k factorial. Okay, and here you have a p to the power k and q to n minus k. Okay, now this k will cancel with 1k from the k factorial. So this really will become k minus 1 factorial. K minus 1 factorial. So I want to change this a little bit. I want to change everywhere there is k, because now something has changed. K has become k minus 1 here. So I want to change everything there is k to k minus 1. The way I can do that is, so this one, k n minus k factorial, can be managed by putting in a 1 here, minus 1, and replacing this, or let's just write that down, n minus 1 minus k minus 1. You see, this is still n minus k factorial, because the minus 1 and this plus 1 will cancel. Right. I want to change this k to k minus 1, but therefore I need to add, or I need to multiply 1p here, because this has index 1, which will add to this and give you k. And this n minus k can be adjusted like before. Excuse me, this will be n minus 1 minus k minus 1. Okay. Actually, this p has nothing to do with any k here, so let's just take that out. I want to take that out. Okay. Also, something more happened. N became, wherever there was n, they became n minus 1. So I want to change this n to n minus 1. And I know how I can do that. I can write n factorial as n into n minus 1 factorial. So there is going to be an n here. But this n has nothing to do with k, which is the summation range. And so I'll just take that out as n. Okay. So now I just have to work out this thing. Okay. There are too many symbols. I want to write k minus 1 as r. R is another index that so let's just write that. So what do I have here? I have n minus 1 factorial. I have r factorial, because I'm writing k minus 1 as r. I'm writing n minus 1, or let me just write m as n minus 1 as well, okay? Because we want to reduce. So this is going to be m factorial by r factorial over m minus r factorial, okay? And this is going to be p to the r. This is going to be q to the m minus r. And now I'm going to change this summation, which was given in terms of k, to k. I'll write it in terms of r now. K ranges from 1 to n, but r is 1 less than k. So r will range from 0 to n minus 1. Okay? It is going to range over numbers which are 1 less than this range, because r is 1 less than k. But this n minus 1 is just m, so I'll just write m instead of this. Right. What is this? This really is if you forget the sum, if you look at this one, so I'll just write it once more. We have np outside. I have a summation which ranges from 0 to m. And I have, this one is m choose r, p to the r, q to the m minus r. That's a PMF. That's a PMF, probability mass function of a random variable with, let's say, y, or I'm already using y. That's if z is a binomial distribution with parameters m and p, then that's the PMF of z. M choose r. This is just P of z. This is just what it is. P of z equals r. M choose r, p to the r, q to the m minus r. Okay. And if you add all the PMFs, so really this is just np summation r from 0 to m. Of course, the spectrum of z is going to be from 0 to m, and that's the range of this summation. So this is just really probability of this random variable, binomial random variable, okay? And if you add all of them, okay, that's just 1, because if you add all the PMFs, okay, you get the probability of the whole set, which is the probability of the sample space, okay, and that's just 1. In other words, you can also think about this as equal to the cumulative distribution at infinity, okay? So this is just 1, okay? So np, and this is 1, okay? I hope that's correct, because this really is f of infinity, capital F of infinity, okay? Just adding all the probability mass functions will give you the probability of the whole sample space, okay? So this is just the probability of the whole sample space PS. This sum will become, okay? And so therefore it's just 1. Some probability of sample space is 1, and therefore this is going to be NP, and that's the problem for you, okay? Right. We'll do the next one. The previous problem was an important result in expectation, because it actually tells you what the average value is if you have a binomial distribution, and you will probably understand that more when we take that up. But because this is an assignment, we're sort of giving problems a little ahead of ourselves, because that also develops the theory. Okay, problem 4. We have a function that is given to us, a function from real numbers to 0, 1, this closed interval. And the function is defined like this. Fx is equal to, I want to use small x to show that it's a real number and not a random variable. This is given as capital A, which is a constant, e to the power minus bx, okay, when x is greater than or equal to 0. And this function is just 0 when x is less than 0. Okay, the question is, for what values of a and b, what are these values, so that f is a PDF, okay, probability density function. What are these values? So that f is a probability density function. So when we're dealing with probability density function, automatically it means that we're dealing with a continuous random variable, okay? Because that's when we use PDFs. Right. So the important result which we have already done is that if you integrate, just like when we added all the probability mass function, it gave us 1, or capital F of infinity, probability distribution function at infinity. Similarly, if you add all of these values, because these are continuous, x is continuous over r, okay? So addition here means really integration. So if you add all of this, in other words, if you integrate fx dx, for this to become a PDF, this should give me capital F of infinity. Okay, this was a condition for a function to become a PDF, and this was one of the properties which we had even looked at. Okay, so this should be 1. Okay, and we know that cumulative distribution function at infinity is 1. So whatever this function is, it better integrate over minus infinity to plus infinity as 1. Okay, so let's just do that. Let's integrate this one. And it should give us 1. Okay, that should give us the condition on capital A and small b. So if I integrate between minus infinity to plus infinity, this function, well, actually there are two segments over which I can integrate, or 2 segments over which the function behaves differently. One is from minus infinity up to 0, any number that is less than 0. So from minus infinity up to 0, I can integrate this function, and then I can integrate the function from 0 to infinity. The reason I have broken this up is because the function values are different over the 2 segments. Over the first segment, from minus infinity to 0, the value of the function is identically 0. So this function, fx, is just going to be 0 over this segment, over this interval. But here, from 0, anything when x is more than 0 or equal to 0, this is just going to be capital A e to the power minus small bx. And this should give me 1. This has 0 contribution because the integrand itself is 0. So therefore the equation which should give me the values of capital A and B is this, okay? This integration of capital A e to the power minus small bx integrated from 0 to infinity dx, this should give me 1. That's what it is. So let's just integrate this. What do I get if I integrate this? If I integrate this, capital A is a constant. Now, there are many possibilities for b, okay? The question is, if b is not 0, then I can write this as minus b, a by minus b e to the power minus bx. That's going to be the integration from 0 to infinity. Okay? The limits will be from 0 to, but this is valid only when b is not 0. Okay? If b is 0, I can't divide by 0. So let's do one case. Case 1 is when b is 0. If b is 0, then this integration is just capital A e to the power 0 is 1 dx from 0 to infinity, and this should be equal to 1. Now, this capital A is a constant. It comes out, and you're really integrating 1 from 0 to infinity. That just gives you infinity equals 1, which is an absurd result. Okay, because this integration is x. Integration of dx is just x. And if you put the limit from 0 to infinity, it just gives you infinity. So this is not possible. Okay, so let's just keep that. B equals 0 is not possible. So therefore, I can integrate it properly in the sense that I can divide by minus b, and the integration of e to the power minus bx is when b is not 0, is that this minus b will come down as a denominator and e to the power minus bx. And because you have the limit 0 to infinity, that's what you put in there. Okay, this should be 1. Now, again, let's check the values of b, capital B. Small b. The question is, we also have to, there's something, so let's say something about A before I go on to check what B can be. Here, if small f has to be a PDF, I'll just write it here. If small f has to be a PDF, then it has to follow the fact that, you see, it's the value of this function, or the range here, the image set of this function is given in this closed interval 0 to 1. So you cannot have this function more than 1 or less than 0. Okay. So if I put x equals 0 here, what happens when x equals 0 is this case, when x can be 0 here. In that case, I'll have what? I will have capital A e to the power x is 0. So e to the power 0 is 1. So I should have f0 as capital A. But since f0 is an image of 0, it cannot be more than 1 or less than 0. So it has to be less than 1 and more than 0 in this interval, okay? Because f0 will be in this range of 0 to 1, including 0 and 1. So we have basically found a range for capital A. We have found where capital A can be. It's a positive number. It has to be, actually a non-negative number. It can be 0, but it has to be a non-negative. So let's just write that down. One analysis shows us that small b cannot be 0. We have found that capital A will be non-negative and less than equal to 1. Okay. Let's do more. So it's a positive number. Okay. Or non-negative number. Okay. Can it be 0? Well, if this is 0, then we have trouble because there is a 1 here. Okay. So there's going to be a problem. Probably it is not 0. Okay. But that all depends on what's going on here. Okay. Now, the question is, can B, third case, can small b be less than 0? If small b is a negative number, okay, then what happens? So this negative will multiply with this negative, this b, since b itself is negative, it has a negative before it, so it's a positive number. The whole thing, so therefore it's e to the power some positive. If, for example, if b is minus 2, then this is e to the power 2x. And if you put limits 0 to infinity on this, where b is minus 2, you get infinity because e to the power infinity is infinity. So if b is negative, you're going to get infinity from the left, which is not possible, because it has to equate to 1. So b cannot be, so this is not possible. So b cannot be less than 0. In other words, b will have to be, so this analysis tells us that b will have to be greater than or equal to 0. Okay. What happens if b is greater than or equal to 0? Then, for example, if b is 2, then this is e to the power minus 2x. Now, e to the power minus 2x really means 1 over e to the power 2x. And if you put infinity instead of x here, that's 1 over infinity, which is 0. And 0 minus 0 from this limit, the lower limit. So now you're getting a 0. E to the power 1 over e to the power 2x. If you're going to put infinity here, you're going to get 0 from the first, putting the upper limit, because you're going to get 1 over infinity. And then when you're going to put 0 instead of x, you're going to get e to the power 0, which is 1, so you're going to get minus 1. So for a positive number, or a non-negative number like this, okay, oh sorry, b cannot be 0, so we've ruled that out. B has to be positive, okay. So for a positive number, this limit actually gives you minus 1. For example, when b is 2, this is giving you minus 1. So, and doesn't matter if it was 3, it would still be minus 1, because really it loses its influence in front of infinity and 0. Okay, so this is minus 1 for B positive. So what we have is, so that minus 1 will mingle with this minus 1 and make it capital A over small b equals 1, which really means that capital A will be equal to small b. Okay, and that's the answer really. So the answer is going to be capital A will be equal to small b, and since capital A ranges between 0 and 1, B should be between 0 and 1. But since B cannot be 0, even therefore A also cannot be 0. So really, this is what the range is for these values, these real number values, where capital A and small b will be between 0 and equal to, less than equal to 1, but they will be equal. Okay, so really, this problem, to be a PDF, has to be something like this. For example, if I call both of them, they're equal. If I call them lambda, they will have to be like this, where lambda is a positive number, okay? And it is also, it's a positive number and is less than equal to 1. So, see, capital A and small b are equal, okay? Like that. So, that's the range. This is what the range is. These values, for these values, this will be a PDF. Okay, we'll do the last one. Which is, again, back to binomial. The question is, we've discussed this kind of an example while we were, we were learning about binomial distribution, is that there is a shooter, okay, who shoots a target with a probability. So a shooter shooting a target n times is going to be a binomial distribution. So we're dealing with a random variable with binomial distribution n and p, where at each turn, each shooting, the shooter hits the target with a probability p. And in this question, it's given that p is 0.9. So the shooter hits the target with probability 0.9. Okay. The question is, how many times must the shooter shoot? So number of times the shooter must shoot to hit the target, okay, n minus 2 times, okay, where n is the number of times the shooter shoots, okay. So here in the problem it's given hits the target 2 less than the number of time it shoots. I'm taking that the shooter hits the target n times, n minus 2 times with probability, or with at least a 50% chance, with probability greater than equal to 0.5 or half. Okay, so since that's a problem in binomial, I'm just going to write with n and p as the parameter. So this is just that the shooter hits the target n minus 2 times with a probability greater than equal to half. That's the equation. Okay, I'm taking n to be that number of times. Number of times is n. Okay. So how many times must the shooter shoot so that they shoot the target, or at least they hit the target at least with a probability half. Okay. And of course, since we're dealing with binomial distribution, this just breaks up to n choose n minus 2, p to n minus 2, and 1 minus p to 2. Okay, n minus 2 is 2. And this should be greater than equal to half. What does this come to? Actually, this is n minus 1 with a 2, with 2 factorial. Okay, 2 factorial is 2. This is p is 0.9, so it is 0.9 n minus 2. and this is 0.1. 1 minus 0.9 is 0.1 square. That is greater than or equal to half. I can get rid of the 2's from both sides. Okay, so you just have this. Okay, 1 on this side. Okay, a bit of a calculation. I can write this as 1 over 100. So 0.1 square is 1 over 100. I can transfer that 100 to that side. So really this is greater than or equal to 100. I can in fact get rid of an 81 on this side. So 0.9, so this will be divided by 0.9 square. Okay, 0.9 square is 0.81. It's just 0.81. I can multiply that onto that side. So really what I have is n square minus n, 0.9 to the n, and on this side I have 81. Okay, so that's the equation. You have to find n at least that many number of times the shooter must shoot so that this equation becomes greater than or equal to 81. That's the answer. You just have to find n from here. Now it turns out in this problem, I had actually asked you to use the calculators and go through what different values of n you can put. It turns out that this, and I've checked this, it turns out if you draw a graph of this, okay, from where you can choose n as a variable, the value of n really starts, it goes up to a certain point. The maximum it reaches is somewhere less than 50 or maybe it's 50, okay, it was 50, 51, somewhere. The maximum it reaches for n more than 0, I mean, okay, I'm plotting n here. And then it sort of goes down like that, okay? It falls and falls and finally reaches 0 as n goes to infinity, okay? This is a factor, this is a decreasing factor. You see, 0.9 to the power 1 is 0.9. 0.9 to the power 2 is 0.81, which is smaller than 0.9. Okay, and if you go on increasing n, this factor is going to fall with a power that is increasing in terms of n. So even if this is increasing, this factor is going to make the whole product fall. Okay, so that's why it falls. But of course, there is an increase initially because up to a certain point, I think, I'm not sure whether it is 18 or 19 or something like that. This is the dominating factor. Okay, this increases more than this factor up to 19, let's say, and then after that this becomes the dominating factor because it's a decreasing factor, and this is always an increasing factor, but the decrease becomes more after 19, and so it falls, and so this is so really. If you're plotting n here, the question is, when will this value be more than 81? The 81 is somewhere up there. The answer is never. Okay, the answer is never. So really, the answer for this problem is that it doesn't matter how many times the person shoots, he will never hit the target n minus 2 times with the probability 50% chance of a probability half. Okay, so really that's the answer. It's a problem. It's kind of a tricky problem. It's a problem where you have to analyze the answer a little bit. I mean, this is the equation. You have to analyze the equation and tell me and what the answer is. And turns out that the shooter cannot achieve the target that's been given to him or her. Okay. All right. So I think, as I said, this was a problem more in analysis than really the particular answer. Okay, we'll finish with this. I hope these problems have come in handy. Hope these solutions will probably shed more light on the topic or the kind of the topics that we have been doing. And as was the purpose of this assignment was to introduce a few topics way in advance of when we are going to do it, and hopefully. When we actually take up the topics like expectation and Poisson distribution, hopefully you're more well acquainted with the topics by just a mere exposure through this assignment. All right, we'll finish it here. Thank you.